Hello everyone and welcome to the next session of our Digital Redays 2024. My name is Silas Zorn and I will moderate this webinar today. We are very pleased that you took the time to participate in our next session. The topic of today is keeping the rhythm, how capacitor selection affects crystal accuracy. Our speaker today is Sarah Moschüz. Hi Sarah.
Hello.
She is working as a product manager at Würth Elektronik eiSos. Before we start with the webinar, I would like to point out one thing. First of all, you will be muted during the session. This means that you cannot ask us questions via your microphone, but you have the chance to ask your questions in the chat. After the presentation, it will be about 30 minutes long. We will start with a Q&A session and then we will answer your questions. If we are unable to answer all your questions within this time, Sarah will answer them via email in the next days. So last information for you. You will all receive the link to the presentation as well as the recording in the next days via email. So now I will hand over to you, Sarah, and I wish you a nice webinar.
Thank you. Also, warm welcome from my side to the Digital WE Days this year. As Silas said, my name is Sarah and I'm working in the product management. And today I would like to talk to you all about how capacitors can affect the crystal accuracy. But to start with, did you know that choosing the wrong capacitors can cause the heartbeat of your circuit to go out of sync? So most of you will know that the crystal is the heartbeat of the circuit. Every heartbeat will need a brain to function. That's usually the IC in the circuit. But also the IC will need the heartbeat to function correctly. Like in a human being, the brain is just working if you have your heart to keep everything in sync. And today I would like to show you how those small capacitors can cause your heartbeat of the circuit to go out of sync. What I would like to show you today, we will start with the Pierce oscillator circuit. Then we will take a look at the load capacitance, moving on to trim sensitivity. Then I will go in more details about how to select the right capacitor, give you more information about the difference of a high or low load capacitance in your circuit. I will give you some PCB recommendations, and last but not least, we talk about series resonance circuits. But first of all, we will get there in a second. So yeah, first of all, we start with what is a crystal. So a quartz crystal is silicon dioxide. Usually you can grow it in the nature. For the use in electronic circuits, they will be grown synthetically. But just with a crystal bar, you cannot use it in a small circuit. So what we do is we cut tiny pieces out of a quartz crystal. We call them blank. We put a silver electrode on it and put it inside a housing. Seal this housing hermetically, so nothing can go in or out. And that's how you get it if you sell a quartz crystal at our end. Yeah. So what is the equivalent circuit of a crystal? So the equivalent circuit contains one branch that is a series resistor, a capacitor, and an inductor. And all of that is in series to another capacitance. Those represent the mechanical damping, the oscillating mass of the crystal, the dynamic capacitance caused by the piezoelectric effect, and the shunt capacitance and coupling capacitance of the crystal. They are caused by the electrodes and the silver we put on them. For further understanding later on, I would like to show you how the specification of a crystal could look like. So the first is you usually have the size. We call that the model, in this case CFPX 180. You have the frequency that you choose, Then the first value is the tolerance. The tolerance is the frequency deviation at room temperature. You have the stability, which is the frequency deviation over temperature range. Therefore, you will need the temperature range for sure. And then the most important value for today, the load capacitance. Then we come to the Pierce oscillator circuit. Like I said on the first slide, a crystal is basically a piece of silicon dioxide. And it's just silicon dioxide with silver on it. So basically, you could call it lazy. To get a frequency out of a crystal, you will need a circuit around it. Therefore, that's the typical circuit everyone is using. So 99.9% of the cases, it's this circuit layout. So you have an inverter, 2 resistors, the crystal, and 2 capacitors. The inverter and one of the resistors is usually already contained in the microcontroller where the crystal is placed next to. So if you design your oscillator circuit, you don't need to care about that. You just place the crystal close to your microcontroller and do whatever information you get out of the microcontroller datasheet. Then for today, we don't talk about the additional resistor RS because that goes too far for today, because we want to focus on the capacitance CA and CB. In every datasheet of a crystal, you will find information about the load capacitance. So for example, in this case, 10 picofarad. But what does this mean? This means the whole capacitance that the crystal sees in a circuit. So every capacitance in this circuit here needs to be equal to 10 picofarads. If it's higher or lower, that will cause your frequency to shift and maybe go out of specification. And how can you now calculate the capacitance in your circuit? Therefore, we have a little formula here. So CL is the whole load capacitance in your circuit, and that needs to match the datasheet. Then you have CA and CB as the values of the capacitors, and then you have the value stray capacitance. So what is important to consider if you select CA and CB? In the best case, CA and CB should be having the same value. This is good because then you have a stable oscillation circuit. If you vary, then they should be really close and CB should be bigger than CA, but really try to make them equal because that prevents you from having other issues. The stray capacitance that you have in your circuit is typically between 2 and 7 picofarads. That will mainly depend on all the lines you have, the conductive paths you have on your circuit. So if they're really long, you will increase the stray capacitance. And it also depends on the input and output capacitance of the microcontroller. So here, that's like the unknown value. So most of the time when you do the design in phase without having a physical PCB, you won't know the exact stray capacitance value. So you always need to guess, is it 2, is it 7, are we maybe at 5? But you can only estimate or confirm how big the stray capacitance is later on if you do a measurement of the frequency. And we will come to that later to see how that measurement works. We have one other case where the formula will slightly change, and that's in the cases if the input and output capacitance of the microcontroller is known. So if the microcontroller datasheet gives you the information about C in and C out, then you can use them as a value in your calculation to make sure you have a proper calculation here. In this case, the stray capacitance will be reduced and it will only be the capacitance of the conductive paths. And depending on how long you make your lines, it will be around 2 picofarads. So you might wonder, why do we make such a big deal of a few picofarads? Because picofarads is really, really small. But 1 picofarad can cause a lot of frequency deviation in a crystal, and a crystal should be there in your circuit to have a really precise frequency. So we have the trim sensitivity as a value, which gives you the frequency deviation in ppm that is caused by a shift in capacitance. So here you can see the formula for the trim sensitivity TS. And in the formula you can see C1, which we saw in the equivalent circuit. We have C null, also from the equivalent circuit, but we also have CL. And CL in this case really means the load capacitance the crystal sees in the circuit. So if you vary CL in your circuit, your trim sensitivity will also vary. So what does the trim sensitivity depends on? It depends on the size of the blank. So how big is the piece of crystal you have in your package? So for you, as an example, I have brought a picture with me of 3 components in 3 different sizes. And what you can see here is that the dimensions slightly vary from size to size. The electrodes vary from size to size. And this causes all those products to have a different trim sensitivity. So to conclude, the trim sensitivity really depends on the size of the blank, size and shape of the electrodes, the load capacitance in the circuit, and also the frequency of the crystal. Because the frequency also depends on the blank dimensions, because the thickness of the blank will determine the frequency. So now I talked about trim comparisons. So I have brought to you 3 different components that we have in our catalog. All of those 3 have 24 megahertz, a typical frequency. They have a tolerance of 10 ppm, means if you use them just at room temperature, the frequency should be within 10 ppm of 24 megahertz. And all of those 3 components have a load capacitance in the datasheet of 8 picofarads. So now we have a standard CFPX 180, 3.2 by 2.5 millimeters. The trim sensitivity with a load capacitance of 8 picofarad is 22.1 ppm per picofarad. This means if the circuit has 1 picofarad more or less in the circuit than those 8 picofarads, the frequency will change by 22 ppm. Remember, we have a tolerance of 10 ppm, meaning if you choose the wrong capacitance value, you will be immediately out of the tolerance spec. So you can buy a really good crystal with a really good tolerance, but if you don't have the proper design in for the capacitors, you will end up out of specification by just 1 picofarad. Another example, a bit smaller this time, 2 by 1.6 millimeters. Even here, we have a trim sensitivity of 10 ppm. So also this component, if using 1 picofarad of wrong load capacitance, will be out of specification already. And then last but not least, we have a really small one, 1.6 by 1.2 millimeters. So one of the smallest ones we have in our portfolio. There we have a trim sensitivity of 6.5 ppm. So in this case, you could be a bit wrong with your design, you could be slightly off with your load capacitance, but you might end up still within specification. But you see as well, it's close. So if you're a bit further away than 1 picofarad, you might be ending up with being out of the specification as well. So to show those values a bit more visual to you, I brought a graph with me today. This is showing the frequency deviations of those 3 components we were looking at over the load capacitance. So you can see on the x-axis we have the load capacitance. So if we vary the load capacitance, how much frequency change will we see? So how many ppms is the frequency changing? In our case, we had 8 picofarad components. So we say if the circuit has exactly 8 picofarads, that's perfectly fine. We have a frequency deviation of 0. So that's the ideal case. But what happens if we would have 10 picofarads in our circuit? Which could happen quite easily because of the stray capacitance, and you made a wrong suggestion by the stray capacitance. So what does this mean for those 3 components? That means all of those components have a negative frequency shift, and all of them are out of specification already. So the biggest one, the CFPX 180, has the biggest change by minus 36 ppm, while the smallest one has the smallest change by 10 ppm. But what happens in the other direction? So we have 2 picofarad less in our circuit. Could be happening as well if we have a better design, less stray capacitance that we expected it to be. The frequency moves, and the frequency is out of specification again. So all of those are again out of specification the biggest size has like the biggest change by 56 ppm. Remember, the part has a tolerance of 10 ppm, so we're like 5 times over the tolerance value. So you could really buy the best crystal if you don't have the right load capacitance in your circuit. Could be the best crystal, but you still have a frequency deviation way higher than the tolerance. And still for the other sizes, it's the same. We're out of specification of the 10 ppm tolerance. So this is why it's so important to choose the right capacitors, because it's really affecting your accuracy. And if you have an application that's needing a really tight specification and frequency, then it's even more important to select the right capacitors. So what can you do then? So what is the tips or tricks I would give to you today to choose the right capacitors? So first of all, you should select a capacitor with a stable temperature behavior. So an NP0 capacitor is the right one to go with. So why do we need a stable temperature behavior? So you need to consider that most of your applications will be affected by a temperature change. So you will have maybe a bigger operating temperature range than just room temperature. And if the capacitance value of the capacitor changes by temperature, that means that the capacitance in your circuit will vary, and we will end up with a frequency deviation like shown in the graph one slide before. So it's really important to choose stable capacitors, because also they will affect your accuracy of the crystal. Then what voltage should you choose? So typically I would say you don't need anything bigger than 25 volt as a rated voltage value. But be careful here and check the microcontroller datasheet. The microcontroller datasheet should give you an information about how much it can vary or how much the rated voltage should be. The other important thing here is you can do all the calculations with the formulas I showed before. You can try to be as precise as possible. You can try to make sure to have the right stray capacitance. You can make the calculation, but you can end up with a result where there is just no capacitor with that value. So due to the E-series for capacitor values, not every value you might need will be available. So just choose the one that is next to the one you need. So the next highest or lowest, depending on what's closer to your value. And then make sure to just check that you measure the frequency afterwards to be sure that you choose wisely. And then another hint, you can use our RedExpert tool to find the right capacitor by going onto RedExpert, looking at the multi-layer ceramics capacitors, and then make sure to find those that you want. So you can select for the rated voltage, for the temperature behavior, and the values you need. So here's a little example for you. We showed beforehand, we looked at crystals with 8 picofarads as a load capacitance, so we use that value as well in this calculation. And we just guess and say, okay, our stray capacitance should be around 5 picofarads. That's the normal value. We should have done our design properly. It shouldn't be that big, but 5 is a normal value. So that means we have 6 picofarads for CA and CB. So we would need capacitors with 6 picofarads. So looking at RedExpert and what we can offer, you can see we could offer 4.7 picofarads or 6.8 picofarads, but not 6. So in this case, choose either 4.7 or 6.8, put them on your PCB, and then try to measure the frequency and see if you're right or wrong and should change your capacitor. And to show you how to really measure it, we here have another tips for you. So if you test the frequency or measure the frequency of your design, you need, best case, an isolated clock output, or you need to measure it with a low capacitance probe. So why is this? We showed, or I showed in the graphs before, that if you change your capacitance slightly by 2 picofarad, you can cause a lot of frequency change. That means if you use a normal probe with a high capacitance, you bring this capacitance into your circuit, which will mean you don't measure the proper frequency of your circuit. You will measure the frequency of the circuit plus the capacitance of your probe. So whatever you do, you won't measure the right frequency. So either you have an isolated clock output where you don't change the frequency, or you should use a low capacitance probe. Then how to measure the frequency? You should measure it with a frequency counter or an oscilloscope. And you need to be careful here because the frequency deviation is in ppm. So your equipment to measure the frequency should be really accurate. So you need to have at least 6 digits, or 8 digits best, to make sure you really measure the frequency properly to then identify if the frequency is good or not. So how can you now know if the frequency is good or bad, or how you need to adjust your circuit? So we have a frequency deviation that we can calculate with this formula. So you measure your frequency in your circuit, like we said before. Then you divide it by the frequency you have in the datasheet. So for example, for those 3 parts we looked at before, you look at like 24 megahertz. You subtract 1 from it, and then times 10/6, to then have a frequency deviation in ppm. And this frequency deviation will tell you what to do with your circuit. So if the frequency deviation is within your tolerance, you're lucky, you made everything right, the component is within the specification you wanted it to be. If the frequency deviation is bigger than 0 and out of your tolerance value, you need to increase the capacitance value in your circuit. So choose a higher capacitor for CA and CB. If it's the other way around, if the frequency deviation is smaller than 0 and smaller than or more negative than the tolerance you have for this component, you should decrease the capacitance value. So use lower capacitors. And that's how you can adjust the frequency deviation. So make sure if you change anything to your design, please measure your circuit afterwards again to make sure that the frequency deviation will be inside of the tolerance of the component that you find in the datasheet. So we looked at the effects of load capacitance. Now we look at the effect, what does it mean if we have a higher load capacitance value or a lower load capacitance value? So a higher load capacitance value might mean bigger than 10, bigger than 12 picofarads. Lower means 8 or lower. So just compare to the values that you could have. So for the current consumption, it means the higher the load capacitance in your circuit, so if it's 16 picofarads compared to 10 picofarads, the current consumption of your circuit will be higher. If you have a lower load capacitance, it's lower. Then we have the loop gain. So the loop gain is an important value to make sure that your crystal is oscillating. So if you have high capacitance values in your circuit, you will need a high gain value. On the other side, if you have a lower capacitance value, you will need a lower loop gain. So for example, if you have a problem with your crystal starting, so it's not oscillating, you would need a higher loop gain, and you can achieve that with having another microcontroller, or you can achieve that by lowering the load capacitance. But be careful, if you use the same crystal and just lower the load capacitance, you will change the frequency. So you also need to select a different crystal with a lower load capacitance. So based on those 2 values, people would say, why should I choose a high load capacitance? Because lower load capacitance seems better for the current consumption and the loop gain. Yeah, but the frequency deviation is way higher the lower the capacitance is. So the trim sensitivity is higher. So as we saw in the graph before, a high trim means if you are out of your load or of your load capacitance specification, you have quickly achieved the frequency to be out of spec. So some people go with a higher load capacitance to have a more precise frequency, even if they selected the wrong capacitors. So what else, or what other recommendations can I give to you to make sure the crystal is working properly? So the first one is keep your traces as short as possible. So as we learned, stray capacitance depends a lot on the traces. So the smaller or shorter they are, the lower the stray capacitance is. Also avoid 90-degree bends. It's better to have round angles. You should place your crystal away from any other high-frequency device or trace, because that can interfere with your frequency and maybe cause the frequency or the crystal to work at a totally different frequency. You shouldn't cross any other signal line, because also that can interfere. And you should have a stable power supply, meaning if the power supply of the microcontroller changes, that can also affect the frequency. What are other PCB recommendations for crystals specifically? You should have an exposed ground area or a guard ring around the crystal. This ground area should be connected to a separate ground pin only for the crystal circuit, because if it's connected to other ground areas, it could be interfered with signals that are on there. So please make sure to have a separate ground. Also, you should connect your two capacitors to ground. And if you have a multi-layer PCB, please don't put another ground area underneath your crystal. Then, as I said before, keep any digital signal lines, power lines, fast switching lines far away from the crystal, because they can interfere with your frequency. Place the crystal CA and CB as close as possible to the IC. Again, this means you have small or short traces, low stray capacitance. That's really good. You should place CA and CB next to each other and really close to the IC if possible. The traces should have the same length, which means you have the same stray capacitance on both sides. And you should put them as far away from each other by still keeping it short. So the first thing is, please keep it short, but if you can, please put them as far away from each other as possible. Now a small excursus to the series resonance circuit, because what we just talked about today, the whole presentation, was parallel circuits, because that's the common ones. Like I said, the Pierce oscillator is 99.99% of the circuits. A parallel circuit means you have reactive components, the capacitors that we talked about the whole presentations today, in your feedback loop. So the parallel circuit means you have a combination of reactive components and a crystal to achieve the phase shift that is necessary. That's the circuit we just talked about. But there is one circuit design that is slightly different, and that's the series resistance circuits. Because in those circuits, we don't have reactive components in the feedback loop. We just have the inverters and the crystal. But what does series mean and why? So don't worry. If you really need a series resonant crystal due to a series resonant circuit, the datasheet will tell you if it's a series resonant crystal or not. So series resonant will be shown in the datasheet, where you could usually find a load capacitance value. In the past, series resonant crystals were used in cases the crystal should be operated at an overtone frequency. So for example, the third overtone of the frequency that the crystal blank has. In those cases, series resonance crystals were used. But nowadays they are quite rare, because there is other opportunities and other components you could use if you want a higher frequency. So the hint here really is the microcontroller datasheet will tell you if it provides a series resonance circuit to you. If the microcontroller doesn't mention series resonant, and if the microcontroller datasheet says to you, we need to design capacitors around it, then you have a parallel circuit and you need to take care of everything we just talked about. If not, if the datasheet mentions series resonant, then please select the crystal that is properly designed for series resonance. So, a summary of what we learned today. So, we learned today that choosing the right capacitor is very important, because even a few picofarads can have a major influence on the frequency of the crystal. So we've seen if you have a few picofarads less or more in your circuit, you could be out of tolerance. So you bought maybe a really expensive crystal with a really good specification, but you ruined it by using the wrong capacitors. So really be careful here to make a proper design. To help you with your designs, we will soon launch a new design kit that will contain crystals from us and also capacitors that are already matching. So you will find in this design kit a selection of the most popular crystals, and then MLCCs from us that will match exactly with those crystals. You will also find more information about which capacitor to use for which crystal, what effects the stray capacitance can have. But with this design kit, you really have the crystals and directly have the capacitors to build your first circuit and measure the frequency and evaluate if you did a proper design. Then we come to a small outlook, because what we talked about is a lot of design work to make sure that you really achieve the accuracy you want to. And a lot can go wrong because we can easily affect the frequency. But what if we don't want that? What if we want an easier solution where we don't have so much design work? Then we can recommend an SPXO, so a clock oscillator. A clock oscillator, you could say, is the integrated version of a crystal, because it means we have still the crystal and we have an IC inside the package that contains the whole oscillation circuit. So the whole Pierce oscillation circuit, the capacitors and everything is already built in to this component. So as a customer, what you need to do is you need to apply a supply voltage here, typically 3.3 volts or 1.8 volts, and then you get the signal that you want with the frequency you selected for the oscillator without having to do any other design. So it's really simple. Not a lot of design work. You just need a supply voltage, you need the oscillator, and then you need to give your signal from the oscillator to the microcontroller. So that's the easier and integrated solution that we also have at Würth Elektronik. So if you're more interested in an oscillator to avoid all the design work and the issues you could see, then I would recommend to you to buy an oscillator. And now we reached the end of my presentation, and I would thank all of you for participating, and if there are any questions, please ask them now.
Yeah, thank you, Sarah, for your interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout from the presentation today. So now you can download it on the bottom on the right side. And then I would say so. And now we start with the Q&A session. So first question, this one. How do temperature variations affect the accuracy of the frequency?
That's a good question. So we haven't talked about temperature today, or we have just a little bit talked about temperature deviations. So first of all, as I mentioned, if there is temperature variations, it could affect the capacitance of the capacitors and therefore the load capacitance and the frequency. But if you use an NP0 capacitor, you should be on the safe side. But at the same time, all crystals have a temperature deviation just based on the fact that the crystal material will have slight changes over temperature. But that's the value you can find in the datasheet as mentioned as stability. So stability is the whole frequency change you will see over the temperature range that is specified in the datasheet. So please be careful if you want to have an application within a certain accuracy that you look at the tolerance, but also look over the stability that is mentioned in the datasheet.
Okay, cool, thank you. Then next question. Do all the information and guidelines also apply to watch crystals?
Yeah, so what we looked at today is mainly megahertz crystals. But a watch crystal is also similar constructed as a megahertz crystal. It has a slightly different shape, and megahertz crystals always, or watch crystals always have 32.768 kilohertz. But everything we said about load capacitance also affects watch crystals. So please be careful with a watch crystal as well.
Okay, cool. Thank you. Then, next question. So, it's a question about page 6. how important is a short distance between CA and CB G&D connection?
It's really important, as we saw on the PCB recommendations. So please keep also those lines really short, because that means that the stray capacitance is not so high. So also be careful, really keep all traces as short as you can, because that mainly means you have a less stray capacitance. If in any case you want a high stray capacitance, then you can not care about that, but I wouldn't recommend that. So please keep the stray as small as possible, because stray is something you cannot really control. You can control the values of the capacitors, but stray you cannot really control. So keep the stray as small as you can.
Okay, cool, thank you. Then, next question. How important is the placement of CA and CB? For instance, between UC and crystal or back to the crystal?
So yeah, I think here again, first of all, keep it as short as possible. The easiest thing most of the time is to place CA and CB between the crystal and the microcontroller, as you saw it on the design recommendations, but it always depends a bit on your design. If you don't have the space or there's any other reasons why it's not working, you can also place CA and CB after the crystal and the crystal in between the capacitors and also the microcontroller. But just make sure to keep the lines as short as possible, because that will again affect the stray capacitance.
Okay, thank you. We have a lot of questions, so it's very cool to see. So now we come to the next question. How can I check the load capacitance in my circuit without knowing the internal tolerance of my crystal?
So if you don't know the initial tolerance of the crystal, so first of all, I will hope that you have a datasheet for the crystal you bought and know roughly in which area the tolerance will be. So will it be between minus and plus 10 ppm, minus 10 or 20 ppm? But the easiest thing for you is really build one circuit, build a board, measure the frequency, and then see what frequency deviation you achieve. And if this frequency deviation is acceptable for you, then you make everything right. But if it's not acceptable to you, then you need to change it by changing the capacitor values. So it also depends on what your circuit needs or what your microcontroller needs. So just make sure that you know how precise your frequency needs to be. And that, as I said with the first question, please be careful to also consider the temperature effect that the frequency can be affected by. So it's both. It's the load capacitance and then also temperature variations.
Okay, cool. Then next question. So next question. Do smaller crystals always have smaller trim sensitivity?
So if we compare similar components, and by similar components I mean the same frequency and the same load capacitance defined in the datasheet, then it's true that the smaller the crystal gets, the smaller the trim sensitivity gets. So you would say a smaller crystal is better than a bigger crystal. But there comes some problems with having a small crystal. So what I haven't touched base on today is that the frequency of a crystal will be affected by the thickness of the blank. So the physical thickness of the blank is defining the frequency. And if you have a really small crystal, like we shown here today as well, the height of the package is not so high. So for example, really low frequencies like 8 megahertz, 12 megahertz, they are not able to be achieved in the really small packages, just because the blank thickness would be just thicker than the height of the component. So there is some physical limitations with going with a smaller crystal. So here you really need to be careful, because not everything is available with a small crystal. And another flaw is a small crystal has a higher ESR. So that means a higher resistance, you would need a higher loop gain again. So it could happen if you go too small in size with a high ESR, that the microcontroller doesn't provide enough energy to start the crystal. So again, it could happen that it's not working then, So please be careful here to make the right selection.
Okay, cool. Then come to the next question. The frequency deviation by using not the exact load capacitance does have no or minimal influence to the drift during temperature variation.
So if we're talking about the drift influenced by the temperature for the crystal itself, then there is no connection between the load capacitance and the behavior of the crystal over temperature. So even if you choose the wrong capacitors or use another load capacitance in your circuit, you will still have the temperature behavior based off the crystal, like you see it in the datasheet. If you have chosen a capacitor with not so stable over temperature specification, then the temperature specification of the capacitor will also affect the frequency, but I guess in this case you were talking about the temperature behavior just of the crystal, and that's not affected by choosing a different load capacitance.
Okay, thank you. Then I would say one last question. How the parameters of the specific capacitor from different production lots can impact on tolerance and stability of a crystal.
Okay, so like I said at the question before, so stability is not affected by the capacitor. So stability is what it is in the datasheet, and you just need to select the right specification here. For the tolerance, it means, yeah, please be careful choosing your capacitors wisely, because every changes in the production lot might cause changes of the frequency or the load capacitance and then the frequency. The tip here is it depends a bit on how accurate your circuit needs to be. So if you have high trim values and you really have issues with not having properly selected your capacitors, then you might need to think about choosing a different one. If we're talking about a component where the tolerance is 50 ppm, you have a frequency deviation of 10 ppm based off the capacitors, then you maybe not notice it because it will still be within the tolerance. But it will mainly depend on the specification of the crystal and also how much the variance by the production lots for the capacitors are. But all those information and the exact specification of the capacitors and how much variation you can see, you will find in the capacitor datasheets.
Okay, cool, thank you. Yeah, all the questions that were not answered live, Sarah will answer them via email in the next days. So now we are finished with the session, and hopefully we see you on the next session of the Digital Weekdays. Sarah, thank you for all the answers and for the interesting presentation. And now I wish you a nice day, and thank you and goodbye.